As mentioned in the last chapter, it's possible that we might choose not to use a rejection region to help us make our decision with respect to rejecting or failing to reject the null hypothesis. When we don't make use of a rejection region approach, then we'll use something called a p-value approach. And this p-value approach to hypothesis testing is somewhat more intuitive. Considering p-values requires that we think of our problem in terms of probability. Definition 13.1 states that the p-value is the probability of observing a test statistic as extreme or more extreme than what was observed. Alternatively, corresponding to an observed value of a test statistic, the p-value is the lowest level of significance at which the null hypothesis can be rejected. So when we're performing a hypothesis test procedure using p-values, we'll start as before by stating the null and alternative hypotheses and specifying our value for alpha. Then we'll compute our test statistic, and then after that we'll use the test statistic to compute the p-value, and we'll compare that p-value with alpha. Then that will allow us to make our decision. So if we revisit the body temperature example and we want to use the p-value approach, the question is, again, should we abandon the common belief that the mean body temperature of a healthy adult is 98.6 degrees Fahrenheit? In other words, is the sample mean body temperature of a healthy adult significantly different from our assumed population mean of 98.6 degrees Fahrenheit? Basically, we're interested in determining the probability of getting a sample mean of 98.2 degrees Fahrenheit or something more extreme in a random sample of 106 healthy adults, assuming that the population mean body temperature is 98.6 degrees Fahrenheit. If the probability of getting a sample mean of 98.2 degrees Fahrenheit or more extreme is very small, then perhaps our original assumption of 98.6 degrees Fahrenheit as an average body temperature is incorrect. If the probability of getting a sample mean of 98.2 degrees Fahrenheit or more extreme is large, then we may conclude that it is not significantly different from the suspected mean of 98.6 degrees Fahrenheit. So we'll start as we did before. We define the hypotheses and specify alpha. From before, the null hypothesis states that the mean body temperature is equal to 98.6 degrees Fahrenheit versus the alternative that the mean body temperature differs from 98.6 degrees Fahrenheit. And again, alpha is equal to 0.05. Then, when we compute our test statistic, we proceed as before, again getting a test statistic equal to negative 6.64. Next, we'll compute the p-value. Remember, the p-value is the probability of getting a test statistic as extreme or more extreme than the one that we've observed. So that means we're interested in the probability that our z-score is either less than or equal to negative 6.64 or greater than or equal to positive 6.64. And that's because, remember, we are doing a two-tailed test. So if we're thinking about equally extreme or more extreme, we observed a test statistic of negative 6.64. Equally extreme is positive 6.64. And so more extreme then would correspond to getting values in the left and the right tails beyond the plus and minus 6.64. In other words, it'll suffice then for us to look at 2 times the probability of getting a z-score that's less than or equal to negative 6.64. If we use a computer to do this, we'll discover that that probability is equal to 3 times 10 to the negative 11. So now, when we go to make our decision, what we're going to do is compare our p-value with alpha. If our p-value is less than alpha, then we'll reject the null hypothesis in favor of the alternative. So here, our p-value of 3 times 10 to the negative 11 is significantly less than 0.05, which is our alpha. So this gives us strong evidence in favor of the alternative hypothesis. So our conclusion is that there's strong evidence to suggest that the mean body temperature of healthy adults differs from 98.6 degrees Fahrenheit. So let me revisit that again. We found that our probability of getting a sample mean of 98.2 degrees Fahrenheit or more extreme was incredibly small, 3 times 10 to the negative 11. Since this probability is so exceptionally small, we're going to conclude that the probability of getting that 98.2 degrees Fahrenheit or something more extreme by chance was very unlikely. Therefore, we conclude our original assumption that the mean body temperature of 98.6 degrees Fahrenheit must have been incorrect.